All right. So last time we were working on some RLC stuff, and I'd given you some homework to do. So I think it was circuit number. Hang on here. I'm going to find that.
885.
345, right?
No, 885.
885. Yes. Okay. So let's put that up on the board and let's get to work on that. I'm going to show you a few things today. Well, you might have heard about it. I think Jerry would have spoken to you about real power, reactive power, and apparent power. Does that ring a bell? Did he also talk about power factor? Okay, so we'll talk a little more about that. So we'll do a few calculations. I'll give you another problem to work on today. And stuff to work on for your homework. In the lab, we're going to start looking at diodes. So one of the things I want you to do is in your book, there's a chapter 1. It's on diodes. You've got reading to do. That's your homework. It's one of your other homeworks. Okay. So we'll read up on diodes. Oh. True. So this problem right over here, we had a frequency of 7 kilohertz. We had a voltage of 5 volts peak. Our capacitor was said to be 56 nanofarads, and our resistor 100 ohms. Okay? So the first thing you would do with this problem, first of all, you would determine XC. So you say XC is 1 over 2 pi FC, so it would be 1 over 2 pi 7 kilohertz times 56 times 10 to the negative 9 farads. And what value did you get for that?
46. 406.
406. So 406 ohms. At negative 90 degrees. Okay? So if we make a vector diagram of that, we would have something that looks like this. We'd have 406 ohms that way, and we'd have 100 ohms this way. Make sense? So we'd have one at 0 degrees and the other one at negative 90. So if we do a vectorial sum of that, you end up with another vector right over here that we call total impedance, ZT. So if we want to figure that out, we'd say, well, Z total is equal to the square root of, well, we'll square our resistance. And we'll square our capacitive reactance. We work that out, and what do you get?
420.
420?
418.1 ohms.
480.
418 now. Oh, okay. So 418. So that's, we've got a magnitude of 418 ohms. So now to find the angle, we're going to say, well, that angle, the phase angle, is going to be equal to the inverse tangent of XC over R. So we're going to take 406. We're going to put it over, around here, we're going to take the inverse tan of 406 over 100. And that's going to give us an angle of
9.65.
9.65.
I got 16.2.
You got 16.
I got
You got how much? Okay, I'm going to tell you what I think, all right? I see this 406 this way, I see 100 this way. I expect this angle to be larger than 45 degrees.
I got 76.
You got 76, I would agree with 76 degrees.
It is 76.
of 76 degrees. So this impedance, oh, negative 76 by the way, negative 76 degrees. Okay? So that's our impedance. Next thing we can figure out our total current. So we've got an AC current flowing through there. So we're going to go, okay, well, IT, which is going to be our total voltage divided, well, this isn't resistance in this case, it's impedance. So we'll go voltage total, 5 volts at 0 degrees, and we divide by total impedance that we found to be 418 at negative 76 degrees. So we'll go 5 divided by 418. So what do we get for current?
12 milliamps.
12 milliamps? So 12 milliamps at an angle, so you go 0, take away negative 76, so 2 negatives is positive, so this is at 76 degrees. So the rule here with the angles is when you're dividing, you take the top one, you subtract the bottom one. All right? All right, so the next thing I'm going to find for you is I'm going to find a couple of voltage drops.
I don't. I'm sorry.
So, first voltage drop is VXC. This one is VR. So, VXC. So, usually when we find a voltage drop, we say, well, current times resistance. So, in this case, we're going to go IT times XC. So, I'm going to go by IT. I'm going to go 12 milliamps at 76 degrees times, we said XC is going to be 406 at negative 90 degrees. All right, so the rule here when we're multiplying, very simple, we're going to take our 12 milliamps times our 406. Do that for me if you haven't done it yet. So take 12 times 10 to the negative 3 times 406. 4.87, so 4.87 volts. Does that work for everybody? Try it out. Try it on your calculator. Don't just take his word for it. It's going to verify everything. And then what we do with the angles, when you're multiplying, you add the angles up. So dividing, you take the top, you subtract the bottom. Multiplying, you take the angles and you add them up. So you got 76 minus 90, so 14, negative 14. You get negative 14 degrees. So the voltage, VXC, is at negative 14 degrees. So if I was going to make a little vector diagram of that, well, I would have a voltage, so let's say this is 0 degrees here, so I'd have a vector just like this, VXC, and I'd be at negative 14 degrees. All right? Now I'm going to predict that the next vector, when I'm going to do VR, I'm predicting the next vector is going to be over here, and it's going to be at 90 degrees. So I predict the next one's going to be at 90 degrees. So I'm going to go VR, and I'm going to go IT times R. So let's see here. So I consider this like 12 milliamps at 76 degrees times R, which is 100 ohms at 0 degrees. So I know my angle is going to be 76 degrees. So this angle right here is going to be 76 degrees. I know that for sure. And then I'm going to go 12 milliamps times 100 ohms. 1.2 volts. 1.2 volts. So I'm going to put that right over here. 1.2 volts. And watch this. This is magic, all right? Kirchhoff's law says that if you add up your voltages in your circuit, so if you add up your voltage drops, well, they should give you your source, right? That's what Kirchhoff always said. Well, it's true. If I take my two vectors and I add them up, they're going to give me my 5 volts at 0 degrees. Okay? The difference in this circuit is we're dealing with sine waves. If we were going to go check with an oscilloscope to see what kind of voltage we have on these components, well, we'd see a sine wave over here, and we'd see another sine wave over here. Okay? One would be the 4.87. This thing would be like 4.87 volts peak, and the other one would be 1.2 volts peak. If you add them up, it's bigger than 5, but you got to remember, they're not happening at the same time. They're out of phase with each other. Okay? So if you're going to draw that, if you're going to look on an oscilloscope, what you would see is you'd see VXC, which is at negative 14 degrees. So VXC would be like over here. And then you would have VR, which would be like, let's say this is 90. Well, this thing would be, VR would be somewhere like this. You'd have 2 sine waves. They're out of phase with each other. One would be at negative 14, lagging, and the other one would be at plus 76, leading. If you took those things, put them in a summing amplifier, they would actually produce one wave at 0 degrees, 5 volts peak. That's what it would happen. Those 2 sine waves, if you could add them together, you can do it with your scope. Put one on channel 1, one on channel 2, put add, and they're going to give you, they add up to be one wave at 5 volts. All right? So the next thing we're going to do is we're going to figure out power in the circuit. So here's the deal. There's 3 types of power. Talk about that for a second. So there's real power, so we'll call it power real. It's in watts. Now, real power is the power that actually does the work. Okay? If there's heat created, if there's motion created, if there's light created, you have watts. That's what it takes. That's what you want, or watts. That's the stuff that you want to harness. Okay? The next kind of power we're going to talk about is reactive. P, reactive. That's the kind of stuff you measure across inductors and capacitors. It is in VARs, volt, amp, reactive. And that's stuff that is stored. It doesn't do any work. It's just stored power. And that's what you find, that's what's stored on the capacitor, that's what's stored on the inductors, reactive power. Now, if you add both of those things up together, so you have one vector in one direction, another vector probably at 90 degrees from it. If you add those 2 vectors up, the sum of these 2 things is called apparent power. P, apparent. And that's in VAs, volt amps. Whenever you get a transformer, if you're speccing out a transformer for an application, it's always rated in volt amps. Because they really expect stuff to be out of phase. Okay? So transformers, for instance, if you've got an application and you figure, you're going to need 30 watts, well, on a transformer, might be rated for 30 VAs. You're going to need at least that, if not a little bit bigger. Just to give you an example, the transformers are always in VAs. And VAs is the sum of real power and reactive power. Okay, so the whole idea with this business here, once you're done with that, there's another thing you can calculate. It's called a power factor. So PF, which we call power factor. And what it is, it's a ratio of real power over apparent power. Okay? Okay, that's your power factor. Ideal power factor equals 1. That means all your power is being used. If you get a power factor of 1, that means all of the power is being used to do work. It's all watts. And that's going to be one of your big responsibilities as an electrician. You're going to be in wherever you're working, you're in just, your shop, wherever you are. One of the big concerns is going to be we've got to have a power factor of 1. And the reason for that is when your power factor is lower, that means you've got some reactive power that's running around in your system. Okay? And that's not a good thing. It's wasteful. For instance, if Hydro One, for instance, are selling power to your factory, okay, they will ask that you have your power factors close to 1. Because if your power factor is off, what's going on is they're sending power over to your place. And if your power factor is less than 1, some of it is bouncing back and coming back to them. And remember, those transmission lines, they have resistance in them. So when stuff bounces back, there's power, there's heat that's generated on the transmission. It's wasted. And what they'll actually do is if you go look up on, I don't know, Ontario Hydro's site or BC Hydro or anywhere like that, they actually have a table that says that if your power factor in your factory is like less than 90%, up 2% surcharge. If it's less than 80%, up 4%. If it's less than, like, they charge you if your power factor is poor. And a lot of power is being bounced back to them. What you want ideally in a good situation is you want the hydro company to deliver power to your outfit, and you want that power to stay there and get burnt. You don't want it bouncing around. So one of your responsibilities is going to be in your factory is to fix it up so that the power factor is 1. So you may have to install capacitor banks or something like this. Most of the time what happens, where you're going to be working, there's going to be a lot of inductive loads, a lot of inductors, motors. So those motors cause reactive power. So what you're going to do to try to nullify that is you're going to install capacitor banks. And they have really sophisticated systems today where they've got like a computer sitting there with capacitor banks, and those capacitors are switched in and out of the circuit to try to keep the factory's power factor as close to 1 as possible. Okay? So let's calculate in our circuit. Let's take a look at what kind of power we have as far as real power and reactive power and apparent power, and then we'll calculate our power factor. So let's start with our resistor. So we'll look at the power on our resistor. I'll give it a fancy, we'll call this one R1 and C1. Okay, so power on R1. So I'm just going to take the current, so IT times the voltage on the resistor. And we can use that one. If we wanted, we could use I squared R. We could use V squared over R. Doesn't matter, you use any formula you want, it's going to give you the same answer. I'm just going to use I times VR. So our IT, oh geez, erased everything. So what was our IT again? It was 12 milliamps at 76 degrees times, what was our voltage on our resistor here? 1.2 volts at 76 degrees. So multiply these two things together. 1.2 times 12 milliamps. Tell me what you get.
.0144.
So what's that in milliwatts and microwatts? What is it?
14.4 milliwatts.
14.4 milliwatts, and this angle is going to be 152 degrees. And I don't really care too much about the angle, but I will tell you this. What you've got here on this resistor are watts. Okay? This is a resistor. It turns stuff into heat, work, watts. Okay? So let's look at the power on XC1. So we're going to take IT times XC. So same thing, 12 milliamps at 76 degrees times. So what did we have for our voltage on our capacitor? 4.87 at negative 14 degrees. Is that correct?
Yeah.
All right, multiply those together. You got 58.4 millibars. And at an angle of 62. That make sense? Hey, what's the difference between the real power? Look at the angle. Here to here. Looks like about 90 degrees, eh? Yeah, they're at 90 degrees from each other. Pretty cool. So because they're at 90 degrees, I'm thinking Pythagoras. So here's what I'm going to do. I'm going to go power apparent. So my power apparent in my circuit. I'm going to go my power real. I'm going to square plus my power reactive. I'm going to square that and take the root of it. So the power real here is, well, this is the real power right here. This is real. This is reactive. Because it happens on the capacitor. We're not burning watts on a capacitor. It's not burned, it's just stored. So it's got to be reactive. So if we do this thing, we take the root of this, we'll go, all right, so I'm going to go 14.4 milliwatts, square that, plus 58.4 millivars, square that. Take the root of this, and that's going to give me apparent power, and I don't really care what angle it's at. We can figure it out, but I don't care. It's going to be between that. So run that through your calculator, and then you're going to come up with some value of apparent power in milli something, milli VAs. Take 14.4 squared plus 58.4 squared. Add them up. Take the root.
60.15.
60.15, so 60.2.
Yeah.
It's milli VAs. Everybody check that, make sure that's okay with you. Is that right?
Yeah.
Okay. So look at that. You got your real amount of power being actually dissipated in the circuit. You've got the reactive power, and you add these two up together in a vectorial way because they're at 90 degrees from each other, and you get 60.2 milliVA. So now, last thing left to do is the power factor. So PF is going to be the real power, so 14.4 milliwatts over your apparent power, which is 60.2 milliVAs. And you're going to come up with a ratio. We'll do 14.4 divided by 60.2. Tell me what you get.
0.2.
0.2? Okay. That's your power factor. 0.2. Not very good, but that's what it is. Okay? All right, so the next thing you're going to do is you take, you've got a page here, you got circuit 225. So now you're going to go to circuit 225, and you're going to repeat everything we did with this circuit. So what you're going to do with that is you're going to figure out, okay, well, this is different. This time we don't have a capacitor, we got an inductor. So our inductor, let me put this up here, is XL. We're going to have an inductive reactance, and the difference here is the formula for inductive reactance is 2 times pi times F times L, and its angle is plus 90 degrees. So with this other circuit, we're substituting a capacitor for an inductor, so we do everything now with an inductor that's at plus 90. So angles that were positive are going to be negative. Angles that were negative are going to be positive now. Okay. So I'm going to ask you to do that little problem. We'll give you about 20 minutes to work on it. So I want all the goodies. I want XL. I want ZP. I want the voltages on the components, VXL and VR. I want real power, reactive power, apparent power, and power factor figured out. Do that now. Yes. 225.